Now let's take a look at a specific example where we use all four methods of estimating the area under the curve. So we'll look at the left-hand Riemann sum, the right-hand Riemann sum, the midpoint rule, and the trapezoid rule. So the function that we're going to estimate is between 0 and 2, and it's a graph y is equal to x squared. So we're going to look at the graph of y is equal to x squared between 0 and 2. And we're going to use a delta x of 0.5. So in other words, we're going to use 4 subintervals. Well, the whole idea is that, okay, well, let's look at 0, 0.5, 1.0, 1.5, 2.0. So these are the x values, and then this is x squared. So these are the y values. So we have 0, 0.5 squared is 0.25. 1 squared is 1.0. 1.5 squared is 2.25. 2.25. And then 2 squared is 4.0. So these are the x values and these are the y values. So if we use the left-hand Riemann sum, LH4, it's going to be delta x times f of 0 plus f of 0.5 plus f of 1 plus f of 1.5. So I use each of the left endpoints. So the first interval is between 0 and 0.5. The second interval is between 0.5 and 1. The third interval is between 1 and 1.5, and the fourth interval is between 1.5 and 2. Now, when you're just given a table and you're asked to compute a Riemann sum, sometimes I see this a lot. Students will use all of 5 of these points given in the table. But these are the 5 endpoints. So these are those 5 points, 1, 2, 3, 4, 5, corresponding to x0, x1, x2, x3, and x4. But there's only 4 intervals. So if you use 5 of them, you're going to get a wrong answer because you're basically approximating the area between 0 and 2.5 instead of between 0 and 2. So for the left-hand Riemann sum, we get 0.5 times 0 plus 0.25 plus 1 plus 2.25. So these two become 2.5 plus 1 is 3.5. 3.5 over 2 is 1.75. So 3.5 over 2 is 1.75, and that's the left-hand Riemann sum. The right-hand Riemann sum is 0.5 times f of 0.5 plus f of 1 plus f of 1.5 plus f of 2. So that's 1/2 times 0.25 plus 1 plus 2.25 plus 4. So that all becomes 3.75. Now I happen to know the exact value of the answer. So the exact area is 8 over 3. So that's my little secret. And you'll see how I computed that later on in the course. But right now you can pretend either that I have a magical oracle that told me this, or that I, in my own time did a Riemann sum with a billion intervals, and it was pretty close to 8 over 3. So, but either way, that's the exact area. And again, there's a very quick way to find this using the power of integration, and we'll see that after we talk about the fundamental theorem of calculus. Notice that this is an increasing function in that the left-hand Riemann sum is definitely less than the exact area, which is less than the right-hand Riemann sum. So the left-hand Riemann sum was less than the exact area, less than the right-hand Riemann sum. So it's increasing function. F is increasing. So that's the left and the right-hand Riemann sum for this particular function. Okay, so next, let's look at the midpoint rule and the trapezoid rule. So the midpoint rule, so we had our 0, 0.5, 1.0, 1.5, and 2.0. So those were our x values. The midpoint rule says, so you can imagine the 4 subintervals and the 4 rectangles. The midpoint rule says for the first rectangle, use f evaluated at 0.25. Use the midpoint. For the second one, use 0.75. For the third one, use 1.25. And for the fourth one, use 1.75. So we can evaluate x squared at those given points. So at 0.25, if we square that, we get 0.0625. 0.75, if we square that, we get 0.5625. At 1.25, we square that, we get 1.5625. And at 1.75, when we square that, we get 3.0625. Very interesting little pattern there. So we're going to use the function evaluated at these midpoints. And this corresponds to, I guess I should have drew it. So let's say we have this curve. These are our 4 subintervals. So the midpoints are the function height right in the middle here, right in the middle. So this is 0.25, this is 0.75, this is at x is equal to 1.25, this is at x is equal to 1.75. So we're using the function evaluated at the middle points to estimate what's going on here. So the midpoint rule with 4 is going to be delta x times f of 0.25 plus f of 0.75 plus f of 1.25 plus f of 1.75. So we're using the middle points for each of the rectangles. So we get 0.0625 plus 0.5625 plus 1.5625 plus 3.0625. Now when we compute that, we get 5.25 and then times the delta x, the midpoint rule gives us 2.625. So that's the approximation for the midpoint rule. So the midpoint rule is 2.625. Now 8 over 3 is 2.66666. So it's an underestimate. And notice that the function is concave up. So for concave up, the midpoint rule should be less than the actual area, and it should be less than the trapezoid rule. So 2.625 is indeed less than or equal to the area, which was 8 over 3, and it has to be less than or equal to the trapezoid rule. Now the quick way to do the trapezoid rule is to recognize that it's just the left-hand Riemann sum plus the right-hand Riemann sum over 2. And we already computed the left and the right-hand Riemann sum, so the quick way here is to just, we get 2.5. 3.75. So the right-hand Riemann sum was, 3.75. Okay, 3.75 plus 1.75 over 2, we get 2.75. So the trapezoid rule 2.75. So you'll notice it's concave up. The midpoint rule is indeed less than the actual answer, which is about 2.66, which is less than or equal to the trapezoid rule. So for a concave up function, the midpoint rule does return a lower estimate, and the trapezoid rule does return an upper estimate for the true value. And notice that it's actually a lot better estimates than the left-hand or the right-hand Riemann sum. because the left-hand Riemann sum was 1.75 and the right hand was 3.75. So notice that we got, with the same number of intervals, we got a lot more narrowed in using the midpoint than trapezoid rule. Makes sense, the trapezoid rule itself is just the average of the left hand and the right hand Riemann sum. So it makes sense that that alone is going to hone in on the value.